Hey guys, just a little video to review some of the topics from first semester that you guys asked about and a couple other things I threw in there. Really, it's just a few of the lecture problems we've done before. Tried to choose some representative examples. But let's dive right in. So we have to write the balance, molecular, and net ionic equations for the reactions between magnesium and cobalt 2 sulfate. This is not too bad. Magnesium solid reacts with, this is going to be in solution, cobalt 2 sulfate. Cobalt's got a +2 charge, sulfate has a -2 charge. So, and this is going to be aqueous. And that's going to yield us cobalt solid plus magnesium sulfate. And that's our molecular equation, and it doesn't need any balancing. It looks pretty straightforward. To do the net ionic, we want to write out everything and then remove all the spectators, right? So magnesium solid plus cobalt 2 plus ion, that's aqueous, plus sulfate 2 minus, and that's aqueous, yields cobalt solid plus magnesium aqueous plus the sulfate ion aqueous. So that's our complete ionic equation. To make it a net ionic equation, we simply strike out the things that appear on both sides. It appears to be just the sulfate. So my net ionic equation would look something like this. Now, what's oxidized and what's reduced? Well, we need to look at what goes up and what goes down, right? You can remember oil rig, or you can remember Leo says grr, but reduced means goes down. So all we got to do is look at the oxidation numbers. Anything in its elemental state is a 0. Anything in its ionic state is its ion's charge. So this is 2 plus. The sulfate we're not going to worry about. It's not in our net ionic equation, so it's not part of the redox reaction. The cobalt goes to elemental, so it's 0. The magnesium becomes ionic, so it's +2. And so which one goes down? The one that went down is the cobalt. Cobalt went from 2 plus to 0. That's being reduced. And so magnesium was oxidized. So magnesium oxidized and cobalt was reduced. That's all there is to that. So I just wanted to review net ionic equations and assigning oxidation numbers. So no big deal there. Now, when we're balancing redox reactions, I don't know if you remember this, but sometimes it gets a little complicated because you have to balance the charges as well. If you look at this one, for example, the charges on the left add up to 0. The charges on the right add up to 6 plus. So we need to move some electrons around to account for that. So this gets a little more complicated. We want to start by assigning our oxidation numbers to the things that are going to get oxidized or reduced. And I can see already that oxygen doesn't even appear on the right-hand side of the reaction. So that's going to be something we're going to have to fix. And that also means we don't have to worry about it being oxidized or reduced. It's going to probably still have a -2 oxidation number, as always. So assigning some of these oxidation numbers is easy because it's just their charge. So this is +2, this is +3, this is +3. But this chromium is going to be, so I've got it's got to add up to 2 minus because it's got to add up to its charge. Oxygen's always a -2, and since I've got 7 of them, that's a total of -14. Now, a total of -14 needs to add to something positive from this chromium, and that has to add up to 2 minus, so I need +12 from this chromium, which means each one is +6. So the oxidation number of chromium is +6. So which one gets oxidized? And which one gets reduced? The one that gets reduced is the one that goes down. So that looks like it's chromium because it goes from +6 to +3. And the iron goes from +2 to +3. So that's going up. So that makes sense that that is oxidized. Okay, but I still haven't balanced the equation, and that's what it asked me for. But I do need to do all this stuff to get there. So let's do the oxidation reaction first. It doesn't really matter, but this is in acid, which means if I need H+, those are available. Remember, we're going to do half reactions on this. So I'm going to do the oxidation reaction first. So let's look at that iron. It goes from Fe2 plus to Fe3 plus. Now I've got to balance the charges. And if I just add 1 electron over here, Now the charges are balanced. So I'm done with the oxidation portion of this reaction. Let's do the reduction part. So this chromium is going to turn into the chromium 3 plus from that 6 plus oxidation number. And so I'm going to have to do a lot of things. I need oxygen, so I need to add 7 waters. And, there's 2 chromiums. I didn't even notice that, so I need to put a 2 there to take care of that. Now I got a bunch of hydrogens on the right that I don't have on the left, but hydrogens are available, so I'm going to put 14 H plus. So now we got to look at our charges. Total charge on the right-hand side is only coming from these guys. It looks like it's plus 6. And the total charge on the left-hand side, I got 14 H pluses, so that's 14 plus 1s, plus the 2 minus, so I got a total of plus 12 over here. So if I want this to balance out, I got to put 6 electrons on the left-hand side, and that'll give me 6 negative charges to cancel some of that positive. So I'm just going to put plus 6 electrons. I just squeezed it in there. Now to get it all balanced, I've got to add these 2 together to get my final reaction. So I'm going to have 14 H pluses, because there's none of those on the other side, plus this guy. I got an electron here and 6 electrons here, so that's going to be 5 electrons on the left-hand side. Plus, don't forget our iron up there. And that is all going to react together to form 2 of these Cr3+, plus 7H2O, plus the iron. Did I get everything? I think so. And that's our final reaction, all balanced up and ready to go. Good idea to double check the total charges. I got 14 positives plus 7 negatives, so that's 7 positives, plus 2 more positives, so that's 9 positives. Here's 6 positives plus 3 more, that's also 9 positives, so the charges balance. We're all done with this. Pause the video, do this one yourself. Do part A, then pause the video here and do part B. Pause the video here, do part C. Pause the video here, do part D. See what you can do. All right, so hopefully you got that. Let's try it. The rate law for this reaction. So remember, the rate is equal to K times the concentration of each reactant, and each one is going to be raised to, so this is going to be NO, and this is going to be H2, and each one is going to be raised to the order of that reactant. So let's look at what happens. If I doubled the NO, what happens to the rate? It looks like the rate also doubles. So that's first order. If I double the H2, here's me doubling the H2, that's the difference between these two things. Oh, yeah. That only doubles also. So that's first order also. So our rate law is just this right here. You don't need to have the ones written. So with the order with respect to NO, that is first. The order with respect to H2, that is first. And the overall order, I don't know if you remember this, but what we do is we take the sum of the other orders. So this is a second order reaction. Good, moving on to part C. Calculate the rate constant. So we're going to try and find K. You can pick any one of these samples you want, but I'm just going to pick this first one. So this is going to be 0.1 raised to the first. This is going to be 0.1 raised to the first. So that's pretty easy. That's going to equal our rate, which is 1.23 times 10 to the negative third when this is the concentrations we start with. So all I have to do is divide both sides by 0.1 twice. So it's just 1.23 times 10 to the negative first. That's K. And that's our rate constant. And the units for K, when we just solve for K, we use that rate, which is m over s, and we divide it by the molarity of each of those two reactants. And since they were to the first order, so it was S times molarity. So one of those molarities cancels, so we're going to get 1 over molarity seconds. We also had a shortcut that said that the units for K, 1 over the molarity raised to the order minus 1 times seconds. So in this case, it was a second order reaction, so the order minus 1, that's just the molarity. So the units are that right there. Here's another rate law problem. Try this one, pause the video, and answer this. We got to find the order for A and the order for B. So remember, the rate is equal to K times, in this case, it's going to be A raised to the whatever order it is, and times B raised to the order of whatever it is. And let's look at what it is. So this one's a little bit harder. When we do this one, they both double at the same time, so we have to be careful about that. Let's look at this one where we just do 4 times for A. So when we look at A here, it goes up 4 times here in this first reaction while B is unchanged. That 2.5 to get to 4.0 times 10 to the negative second, right? That's like 25 into 400. That's 16 times. So we went up 4 times to get 16 times. That means it was squared. So that's a second order. The 4 was squared to get the 16 times, right? It was increased by that much. Now let's look at B, knowing that that's 4 times. So this is B doubling, and this is doubling. So if this doubles, it should go up 4 times because of A. How much is it going up overall? This is 4 going into 32, so that's 8 times. 4 of the times is from A, so 2 of the times must be from B. So we doubled B, and we doubled the amount it went up because of B. So that's going to be first order. When you double and you double, that's first order. So the overall order of this reaction should be third. This is a third order reaction. Now, this is the same reaction, but I got a little bit different question. See if you can answer this one. Pause the video. So when we look at this, we need to get 2 A's and B. So we know the rate law from this part is this guy right here. A is second order, B is first order. So I want to look for 2 A's and 1 B. We want to find that in the slow step. Remember, it's the slow step that determines the rate. So here's the slow step on this one. We've got, it looks like it's going to be, so this is going to happen very quickly. B turns into Y, so you can basically say this is B. So that's basically B plus A, which that's the slow step, but that would be first and first for B and A. So that's not the right reaction. We need it to be second order for A. But if you look at this one, A plus B makes Y, and then Y plus A, that's our slow step. So this happens very quickly, so we don't have to worry about that. And that quickly makes Y. And so we need 2 A's and a B to make this slow step happen. And that's exactly what we've got up here. It's what we got from the previous page when we found the rate law. Second order with respect to A, first order with respect to B. Here's another one. I've got 3 questions down here at the bottom. Pause the video and give them a try. So when we're looking at the order of the complex reaction, again, we have to look at the slow step. So here's our slow step. That's going to determine the order of the overall reaction. What do I need to make this slow step happen? I need 1 of these, and I need 1 of these. Now, these come from this fast step that happens very quickly. So I need 2 of these to make that, and I need only 1 of these. So it's going to be second with respect to this and first with respect to this. And so what order is a complex reaction? It's third. Second with respect to the NO, and first with respect to the H2. What are the intermediates? Intermediates include everything that's not at the beginning and the end, right? So it's everything that's not on this complex reaction. So the N2O2, that's an intermediate. What else? I see N2O is in there. We got water, but that's in this. We got N2, that's in this. Everything else is up at the top. So it's these 2 are intermediates. And the rate law for this reaction is going to be rate is equal to K times NO to the second times H2 with no exponent, because that is first order. There's our 2, there's our 1. That's our total of third order reaction. I got a graph. I got a few questions. Pause the video, answer the questions. So how many elementary steps are in this reaction? It looks like we do one thing here, and then we do another thing there. So 2 steps to the reaction. We're going to have some intermediates that happen at 2. What is the rate determining step? The slow step. That's the one with the highest activation energy. So the activation energy for this one, right, is only this much. The activation energy for this one is much bigger. So it looks like the first step is the rate determining slow step. The intermediates, like I said, are here at 2. And where are the transition states? Those are those moments when one thing is becoming the other thing, and that's happening at 4 and 5. Those are the 2 transition states. All right, jumping on to another unit here. how many electrons does each of the following have? And if you look at this as a sodium, I'm going to go to my periodic table. Sodium normally would have 11 electrons, but this is a sodium with the +1, so it's lost 1, so it's 10. Nitrogen normally has 7 electrons, but in this case it's gained 3, so it has 10. I detect a pattern. This is 10 because it's magnesium, which would normally have 12, but it's lost 2. Give it that +2 charge. Oxygen gained 2. Neon has 10 all the time. It's noble. And the fluorine picks up 1 electron to have 10. So they'll have the same number of electrons. Put them in order from more protons to fewer protons. So the one with the most protons is going to be magnesium. Then we're going to go sodium. Then we're going to go neon, fluorine, oxygen, nitrogen. Put them in order from smallest to largest atomic radius. So these guys all have the same number of electrons in the same shell. They've got the same number of shells as our neon here. They're basically a full shell. But some of them have more protons, and if they have more protons, that means they're going to pull harder on that shell. That effective nuclear charge is going to be greater. Remember our old friend Zeph? That's our effective nuclear charge. And remember, that's the key to all of the periodic trends, really, is how strong is that effective nuclear charge. That's based on how far out those shells are, because there's more shielding of that nucleus. So smaller means we have a stronger nuclear charge, and bigger means it has a weaker effective nuclear charge. And of course, it matters how many protons you have. So put them in order from smallest to largest atomic radius. So the one with the greatest number of protons is going to pull hardest on that shell. It's all the same shell, all the same number of electrons. The one with the largest number of protons is going to have the strongest Zeph, and therefore the smallest atomic radius. So this order is going to look just like the one above. Nitrogen is the largest one here. We've got the same amount of electron shielding, right? Because the shell is the same, but the nucleus is not pulling as hard because it's only got 7 protons as opposed to the magnesium, which has 12. So that effective nuclear charge is smallest on the nitrogen. It's greatest on the magnesium. And that's what makes their ionic radius a little different. Technically, this should be ionic radius for all of these except the neon, but that's all right. Pause the video, answer this question. So the first ionization energy of calcium, it's harder to get that electron away from the calcium than it is from potassium. It's that same 4s shell. So they're the same distance, but calcium has 1 more proton. So again, that effective nuclear charge makes it harder to take it away. But then when you get to the second ionization energy, it's much, much easier to get the second electron off the calcium because it's still taking from that same shell that's way out there. Whereas potassium's second electron, it's from the next shell in, so it's a lot closer to the nucleus, so its effective nuclear charge is much greater. So it's a lot harder to get that off. Remember, it's not just because it has a full shell. Right? Having a full shell doesn't make it extra powerful. There's no bonus attributed to a full shell. It's because we went from a larger shell to this innermost shell with the potassium. With the calcium, we were at the largest shell for the first one, and we're at that large shell for the second one too. When you go to take a third one from calcium, now you're going in a shell. The amount of energy required is going to spike. Photoelectric effect. This is Einstein's equation. The energy of a photon is equal to Planck's constant times, and this is nu, right? This is not a V. If you have to write this out on the AP exam, which I don't expect you will, but if you do, you should write nu. Type out nu, don't put a V, right? Because that's not really a V. And nu, of course, is frequency. This is Planck's constant, which is on your equation sheet. It's 6.626 times 10 to the negative 34th joule seconds. And like I said, this is the energy of the photon. And so this is just a 3-variable equation that you're going to have to rearrange and solve for variables. I don't expect you'll have to do this because they said you can do all the math without a calculator, and you're not going to be doing anything with this number without a calculator. So I don't anticipate that's going to appear on this test. But if you want to, go ahead and pause the video, try these. But all you're going to do here is you're going to plug that in for frequency. You're going to solve for E. This one, you've got a specific number of photons. Each one has the energy you calculated in A. You just multiply and get that. If the laser emits this much energy during a pulse, how many photons? So you're going to take this much energy and divide that by the energy per photon, and that'll tell you how many photons. Because you need a calculator for doing these kind of calculations. Again, this is not the kind of problem I expect to see on our exam. You'd need a calculator for these, so they're not going to do this. I think we looked at this enough times that we're pretty good at these. But there weren't any problems in the free responses I've been giving you that had this yet, so I thought I'd go ahead and throw this in here too, since I was in this same PowerPoint. We're talking about ionization energy. Sometimes they call this binding energy. It's just the energy that it takes to get these electrons off. So we're blasting an atom and knocking off electrons. And as the electrons come off, they're going different speeds based on how much of the energy it took to knock them off. If it took most of the energy to knock them off, then they're going to be going slower. If it took very little of the energy to knock them off, then they're going to be going faster. So they're going to spread out from the ones with the lowest binding energy. Those are your outermost electrons, to these guys here, which are your innermost electrons. Notice the scale goes from 0 on the right to the high numbers on the left. So, but this is our first 2 electrons. So this is our 1s shell. Here's our 2s shell. Here's our 2p shell. Here's our 3s shell. Here's our 3p shell. And here's our 4s shell. So you should be able to figure this out. I've got what appears to be 2 electrons here. Of course, 6 electrons here is 3 times as large. Because this looks like 2 electrons, the same as the rest of these S shells, I can tell you that this is calcium. And hopefully you can do that pretty easily. I wouldn't be surprised to see one of these graphs on there. So hopefully that's helpful to you guys. Just a little walk through some of the things we haven't talked about in a while. If you have any more questions, please shoot me an email. Give me something else to talk to you guys about. Otherwise, we're just going to practice more free response questions. You're doing great. Hang in there. I'm pretty excited about how you guys are going to do on this exam. I think you're going to do well.